Swayam Prabha. Digital India. Educated India.
Hello, welcome. So we have discussed spike timing dependent plasticity, and so now we will be discussing the general approaches that have been used in terms of computational modeling involving plasticity. So, first of all, we will allude or rather go back once more to our general integrate and fire model, just to remind ourselves. And so, if you recollect, we had this idea that you have a capacitor, and then for the leakage we have G leak and then E leak, and we have an I external that can drive this. So, in this model we had removed the sodium and potassium channels that were present in the Hodgkin-Huxley, and also if in other models where we have other kinds of channels, those are removed per se for now to make the most simple possible kind of neural model. So, this is our E leak and we have the capacitance, and so in this case what we know is that if we drive this system with I external of a certain shape or certain profile. So, this is time and this is current I external. Let us say I external is 0 here initially, and then there is some positive current injected, and so accordingly over here we will model the voltage across the capacitor, and that will integrate and reach a threshold that is pre-decided, and we assign an action potential once it reaches threshold, and we reset the voltage below, and we get an action potential whenever there is a threshold crossing, and this leaky integrate and fire model is very useful when we are trying to model activity, mainly rate based activity that to explain behavior of an entire network or some kind of learning and so on. And when precise spike timing is not important in terms of the question, then these kind of models are very useful, and in fact this can be further reduced to an even simpler model, where we say that we have one output neuron whose activity or firing rate is given by V, and we have a set of input neurons. Let us say this is U1, U2 up to U NB, and there are synaptic inputs onto the output neuron, and each of these have weights W1, W2 and WNB. So, basically what we have is the input activity is represented by U1 up to UNB, and hence we can represent it with a vector U, and that is the rate responses or the rate of inputs of the presynaptic neuron. And the postsynaptic neuron V takes these inputs. Basically we have a weighted. So, W is now a weight, that is a vector which is made up of the elements W1, W2 up to W NB, where NB is the number of inputs. And what we are representing by this W is the synaptic strength, and each of the input rates are modified by this synaptic strength, and a proportionate some activity is being added on to the V output. That is, we will say that our V is changing. Let us say we have a dV dt, that is the output V is changing with the time constant tau, and that is this, and we have input W dot U. So, sorry, this is our V and this is a plus W dot U. So, the V is relaxing to go towards a steady state value, that dV dt is 0 with a time constant tau, and is being modified by this W dot U. So, I mean simplification or conversion of the integrate and fire neuron can, with certain assumptions, can be shown to be of this form when we consider rates as inputs and not spike timings or spike trains as inputs. So, what we are saying is that the output potential is always trying to go towards a steady state value if where dV dt is 0, and basically a 0 steady state value when there are no inputs. And when there are inputs, its V is increased by the rate of the inputs. And now this time constant of relaxation is extremely small. It's very or rather we will say that it is reaching there quite fast, I am sorry, so that our dV dt is quickly reaching 0, and in that case our V can be set to be simply the dot product of W times U. So, if we have this as the model, then now we consider what we have learned from our Hebbian plasticity, that is now V equals W times or dot product with U. What our Hebbian plasticity suggests is that if the weights increasing, that is our dW dt is proportional to the correlation of V and U. So, V times U, and there is a time constant based on which, I mean, that is the dynamics of the W, how it reaches the changed value, and this is happening, this tau W is much larger than how the patterns of input are being presented. So, the weight is changing slowly. So, W the weight is slow changing, and there are a number of inputs that are coming in by the time W is changing. So, the overall tau W dW dt then would be represented by an average of all the patterns of input that is being provided. So, time average or the based on all the inputs. So, with this as our learning rule, that is, we have the average of V times the U driving our weight change, or the larger the correlation or larger the product value of V and U, larger is the increase in W. So, what are the sort of consequences of such a learning rule? So, this is what the basic Hebb rule is, but as we will see soon that there are a number of issues, a number of problems with this overall idea, and we will need to modify this gradually to other forms which may or may not be biologically based, and actually the course of development of implementation of plasticity in fact went out of hand just because it became more like a mathematical treatment rather than treatment based on the biology. So, anyway, let us see how this progress went on. So, if we now consider that the W weight, how is it changing? So, let us say we consider tau W dW dt. What is the average of VU? Average of VU is, or rather, we replace our V by W dot U and then U and average of that. So, essentially what we have here is here we have a vector W. So, let us consider just one element of W, that is dWb dt, and that will be the average of. So, when we are talking of this Wb dt, this is a dot product. So, it is a scalar. So, here we only consider Ub, that is one particular input, and so here what we have, this is Ub times summation W I U I equals 1 to Nu, and we are averaging this. So, now as you can see, when we average this, we will end up averaging the correlations in U within the input, that is U B prime U B or U I B, U I U B. So, let me not write it in this manner here with two averages. We set the summation, let us say we make it B prime equals 1 to Nu, and we have W B prime U B prime, this sum, and we have only U B here and the average of that. So, obviously, here what we are seeing is W B. So, each of these terms the summation can come out, and we will have summation B prime going from 1 to Nu, and inside we have W B prime and average of U B prime U B. So, this U B prime and U B, sorry, this average. So, basically with this W outside, W B prime outside and its sum, you can easily show that this dW B dt, or rather the whole now let us write the whole thing, dw dt will be the input correlation matrix Q times W. So, what we have in Q are the elements. So, let us write it here. So, what do we have in Q? Q has basically at it's a NB by NB square matrix, and we are multiplying this by WB. So, we have W1, W2 up to WNB, and here we have average of U1 up to so we have, so basically each of these terms are average of the product of the input rates, or input rates in each of the input neurons, and so this is the correlation matrix. So, and so this is also called the correlation based learning rule, and now if we want to analyze this further, you can easily see here that the dw dt that we have, if we constrain the rates to be positive, our increase in weights is always positive and it keeps on increasing throughout, and there is no way for even implementing long term depression in here. So, this is a unidirectional change in weights. So, given V and U are positive, so it is simply not possible to have any kind of decrease in weights, and all of them will keep on increasing. So, in general this would fail, and so essentially it is sort of a runaway kind of model where the weights keep on increasing, and so ultimately what happens is that it is an unstable situation that is created. So, in order to modify that, so we do not have LTD in the correlation based model. Rule, not model, correlation based rule. So, what is introduced in there is dw dt, that is how the rates are changing with time, again with the same idea. We have either V times U minus theta U and average of that, or we can have tau W as dw dt equals average of, so this theta U is a vector, V minus theta V times U and average of that. Okay. So, what we mean here is that we are introducing a threshold. Threshold in the sense that when the activity V is above or greater than theta V, in that case we have potentiation. So, I am talking of the second form, which is this one, and when the output is lowered below the threshold, we get depression. So, we I mean with this we are getting the the possibility of potentiation and depression. And similarly, in the other case, which is the first case, again we are setting a threshold theta u for each and every input, that is those are the elements of the vector theta u, and so we are getting we would get potentiation or depression based on the input activity at each of the synapses. We can have both of them. It gets the mathematical treatment gets a little complicated when we have theta u and theta v, both of them in the system. But our treatment here that we will do is following the one of the two here, which is tau w, let us say dw dt equals the average of v and u minus theta u. Now, this is a vector. So, now what is our average of v times u minus theta u? So, again if we write, so essentially what we are having here is our v is going to be, so v u is our output, I am sorry, w times u is our output. So, we write w dot u times u minus theta u. So, here if we represent our theta u, if we choose our theta u to be the average of u, then what we get is u minus average of u multiplied by w dot u, actually sorry, so our v has to be not v times u, but v has to be w times u, but w times u minus theta u, because we have done a thresholding. So, I am sorry about this part. Let us say our w times u minus theta u. So, essentially if we choose, so here also we change this u to u minus average of u. So, this turns out to be, if we take the product of these two and average them, the w goes out, and what we are left with is our covariance matrix. Let us say we name it C, because it is the average of u minus the average of u and u minus the average of u, which is the definition of the covariance matrix. And so, our learning rule then becomes a covariance learning rule, that is tau w dw dt is equal to our C dot w. So, now that we have derived this again, although we get LTP and LTD, both of them in these two learning rules, the problem again is that the dw dt is always positive, and that makes this stable. So, the increase in I mean if we take the why would we say that? That is because if we take this rule, tau is equal to dw dt equals c times u, c times w, Let us consider how the norm of the weight changes with time. What we will get is, it is simply a W 2W times dW dt, which is 2W times our CW, and so that again brings that the norm is always positive. So, the overall, even though we may get decreases in one or other of the W, the overall norm keeps on being positive, because we get a W squared multiplying the covariance matrix. So, in this in both these models, which are Hebbian and either correlation based or covariance based, we have a problem, the main problem being that it is unstable, and also there is no competition among the synapses, which is something that is observed in actual neurons. That is, when some synapses strengthen, other synapses weaken to maintain sort of level of activity. And so, without the competition, again this is there is a blow up of this kind of output activity. So, in order to compensate for these kind of problems, there are various methodologies that have been adopted, and in the next class we will be continuing our discussion on implementation of long term potentiation and long term depression, starting with these kind of simple just multiple input single output cases, which can later be generalized to more number of neurons. Thank you.